Hello everybody and welcome to Capacitors lesson 3. In the last video we had a look at the definition for capacitance and you can see over there on the right hand side. So capacitance is defined as the charge stored per unit potential difference. Now what that gives us is the equation C is equal to Q over V. We then looked at energy stored in a capacitor, and the main equation we've got was a half QV, but of course we can do a little bit of rearranging on that, and we can also have that E is equal to a half CV squared, or E is equal to Q squared over 2C, and they were really just rearrangements with a little bit of substitution of those two equations there. Now in this video we're going to have a look at capacitor discharging, and we're going to have a look at the equation that governs that. Now as a little bit of a warning, this is going to be quite heavy on the mathematical side of things, especially if you don't do further maths. There may be a little bit of the maths later on that might be slightly beyond what you know at the moment. But really just bear with me. If you really don't understand some of the maths that we're doing, it's not that necessary for the course. You don't have to know the derivation or anything like that, but you definitely need to know and understand how to use the final equation that we're going to get out of this. So in order to have a look at capacitor discharge, then firstly let's set a couple of things up. Let's set ourselves up just a nice simple circuit just with a capacitor, and we're just going to put that capacitor in series with a resistor, and we're just going to put an ammeter in the circuit as well, and hopefully we'll see exactly why we do the ammeter in a moment. Now let's have a look, think about what's going on first. So initially we're going to say that the capacitor is fully charged. Now of course if that's the case, when we're talking about initially, what we mean by initially is at a time is equal to 0, and what we're saying is that we've got some initial charge, and we're going to call that Q0, and of course if the capacitor is charged then it will have a potential difference across it of V0. Now of course as soon as we connect this circuit together we've got a complete circuit, and of course with the capacitor we will have one plate which will be positively charged and one plate which will be negatively charged. Now obviously with that, what we're going to get is, as soon as we connect the circuit up, we're going to get a current flowing. Now of course remember that the electrons are going to flow that way and the conventional current will flow that way, because of course the reason why that happens, if we have a look at the two different plates of the capacitor, there is a potential difference between them, and if there's a potential difference it will cause a current to flow as long as we've got a complete circuit. So therefore we will get a reading on the ammeter. Now of course that current also is going to flow through the resistor, and we can at least say that at first, and in fact to be honest at any point, obviously the current flowing through that resistor, and we can then say that the potential difference will be equal to the current times the resistance, as in Ohm's law as usual anyway. Now of course what we need to realise with the potential difference that I've written here is that the potential difference, bearing in mind that there is only a capacitor and a resistor in the circuit, the potential difference across the capacitor will be the same as the potential difference across the resistor. So at that point we don't necessarily need to differentiate whether the potential difference is the potential difference across the capacitor or the resistor. Okay. Now we need to think about this current in a little bit more detail. Depending on the charge on the capacitor, we will get, as we've just said, a current flowing. But obviously what the current is doing is it's taking charge away from the negative end of the capacitor and placing it onto the positive end of the capacitor. So as the current flows, the total charge that's left on the capacitor will decrease, and therefore the potential difference across the capacitor is going to decrease as well. But of course, current depends on charge in the first place. So as the current starts to decrease the charge, well, the charge decreases, and therefore the current will decrease as well. But of course, the current decreasing is making the charge decrease even further, and we're in a bit of a sort of catch-22 situation where we've got two things that are affecting each other. Now, what I want to do, I want to take obviously the Ohm's law, the V equals IR, and I just want to rearrange that to make I, the current, the subject of the equation. Now obviously we can do that very easily. That's just I is equal to V over R. Next then, I just want to obviously remind us of the capacitance equation, which is C is equal to Q over V, or rearranging that to make V the subject, we can say that V is equal to Q over C. Now if we substitute that V into the equation here, what we end up with is that I is equal to, well, here comes the substitution, Q over C over R, and tidying that up a little bit, we get I is equal to Q over R times C. Next then, we can obviously think about, and going back to that conversation about exactly what the current is doing in this situation. And going back to our initial definition of current, well, I, we know, is delta Q by delta T. It's the rate of flow of charge. But of course, we now need to contextualise this a little bit. We need to understand what's going on. Well, of course, this charge is the charge on the capacitor, and we know from exactly what we're doing, we're discharging, and therefore we know that this value is decreasing. And what that means is that into our equation here for current, for this particular context, is that we need to put a negative sign in there to denote that the current is causing the charge on the capacitor to decrease with respect to time. Now, everything on the last slide, regardless of your sort of mathematical ability, that bit you need to understand. And what we're kicking into now is really the sort of nitty-gritty derivation of this. So if you don't necessarily get what I'm about to do fully, then don't necessarily worry about it. What you need to understand, though, is the final product. Now, what I'm going to do, I'm going to bring forward those two ideas. So to do with current, so I is minus delta Q by delta T, and I is equal to Q over RC. Now, of course, hopefully by now you can already spot that I'm just going to make the right hand sides of both of these equations equal, because they're both equal to the current. What we end up with then is that minus delta Q by delta T is equal to Q over RC. Now let's do a little bit of rearrangement. Firstly, I'm going to multiply both sides by delta T, and I'm also going to divide both sides by Q at the same time. So what I end up with is minus 1 over Q multiplied by delta Q is equal to 1 over RC multiplied by delta T. And then what I'm going to do as well, I'm just going to multiply both sides by minus 1, simply to shift this negative sign over to the right hand side. So we end up with 1 over Q multiplied by delta Q is equal to negative 1 over RC multiplied by delta T. Now at this point what we're going to do is we're going to turn this equation into an integral equation. So we're going to integrate both sides. Now I'm not going to get into the technicalities of why we can just swap out delta Q and delta T, and when we turn it into an integral we're going to end up with dt and dq instead. Really that's going sort of, at least those technicalities are going way beyond A level. But anyway, what we end up with is an integral of 1 over Q, and sorry I said it wasn't delta anymore. It does of course become dq is equal to the integral of minus 1 over RC dt. Now the first thing I'm going to do with this is we're going to put some limits on here. So we're going to say, going back to the definitions we had on the last slide, that at t is equal to 0 we have a charge of Q0, and sometime later t we will have a charge remaining of Q. The final thing we've got to do with this integral is we just need to note that this bit here, this negative 1 over RC, well, all of those are constants. They don't relate to time at all. They're not functions of time at all. So we can obviously bring those out at the front of the integral. And what we're left with then is the integral of Q0 to Q of 1 over Q dq is equal to minus 1 over RC integral from 0 to t of dt. So to bring that forward to a new slide, then now it's time to do the integration itself. Now when we integrate 1 over Q with respect to Q, what we're left with is the natural log of Q. And again, we're still going with our limits from Q0 to Q. We've still got our minus 1 over RC bit there. And of course, what we're doing here is we're effectively integrating 1 with respect to t. So we just get t, and we're still going from 0 to t. Let's now do our limits. So on the left hand side, what we've got now is the natural log of Q minus the natural log of Q0 is equal to minus 1 over RC, and then on this side you get t minus 0, which of course just ends up as t anyway. So tidying this up again just a little bit, we've got natural log of Q minus natural log of Q0 is equal to minus t over RC. Now on the left hand side what we're going to do is we'll just tidy that one up a little bit. Whenever we subtract logs, it ends up as 1 divided by the other, so that ends up as natural log of Q over Q0 is equal to minus t over RC. Next then we are going to take the exponential both sides. We're going to just raise both sides as powers of e. So if we do it properly, e to the natural log of Q over Q0 is equal to e to the power of minus t over RC. But of course, whenever we've got this, whenever we've got e to the log of something, they basically cancel each other out, again, without getting into the technical math side of this. And what we end up with is Q over Q0 is equal to e to the minus t over RC, and then just finishing this off by multiplying both sides through by Q0. So we get the equation Q is equal to Q0 e to the minus t over RC. And there then, if you haven't followed that, now's the time to sort of tune yourself back in. That there is the capacitor discharge equation. So bringing that forward to a new slide then, we've got the equation Q is equal to Q0 e to the minus t over rc. Now this type of equation, especially when we get e to the power of minus something, is known as an exponential decay. And if we were to draw that on the graph, so if we were to draw a graph of charge as a function of time, then what the graph will look like is shaped like that. So an exponential decrease, an exponential decay, where that value there, that initial value, so when t is equal to 0, we have an initial charge of q naught. Now, of course, this equation can be changed. It doesn't just apply to charge. If you remember that I is proportional to delta y is equal to, really, delta q over delta t. So we get rid of that proportional sign. What we can see, therefore, is that I is proportional to q, so current is proportional to charge. So we can again write this equation instead as I is equal to I naught e to the minus t over rc. So it doesn't just apply to the charge, it also applies to the current as well. And again, when we note that V is equal to IR, and therefore potential difference is proportional to the current, therefore we can also say that the potential difference, and don't forget that will be the potential difference across the capacitor, V will be equal to V naught e to the minus t over rc as well. So here then is your question for this video. A 2000 microfarad capacitor is charged to a potential difference of 6 volts and then discharged through a 50 kilo ohm resistor. Calculate A, the initial charge stored by the capacitor, and B, the current flowing through the resistor after 3 minutes. So go away, obviously pause the video, have a go at this, and then come back when you think you've got an answer. So for A then, this is the relatively simple one. We're just going to apply the equation. So C is Q over V, or in other words, Q is equal to C times V. Well, the capacitance is 2000 microfarads, so 2000 times 10 to the minus 6, and multiply it by the potential difference, which is 6. And what that gives us then is 0.012 coulombs, or of course, again, if you prefer the SI prefixes, you could say that that is 12 millicoulombs. For B then, we need to do a couple of different things here. First thing we need to do is we need to calculate the initial current. Well, the initial current using Ohm's law, so obviously remember that V equals IR, we can therefore say that I naught is V naught over R, which is 6 over 50 kilo ohms, so 50 times 10 to the 3. And what that gives us then is 1.2 times 10 to the minus 4 amps. Again, or of course, we can quite happily write for that 120 microamps. So we've got the initial, and now what we need to do is just plug it through the exponential equation to get our answer. So I is equal to I naught E to the minus t over rc, so it's 1.2 times 10 to the minus 4 multiplied by e to the minus, well, of course I know I didn't really talk about units earlier, but by now we should know that we don't work in minutes, and obviously this is now going to be 180 seconds in base units, so minus 180 divided by, well, again, we'll just plug the numbers in, so R is 50 times 10 to the 3 multiplied by C, which is 2000 times 10 to the minus 6. And the calculator, once we've done a little bit of rounding, it ends up as 1.9835. So if we call that 1.99 times 10 to the minus 5 amps. Sorry, I've actually rounded wrong on that. It shouldn't be 1.99, it should be 1.98. Or, of course, again, using SI prefixes, that works out as 19.8 microamps. So to summarise the lesson then, in this video we've looked at capacitor discharge, and we've ended up with the equation Q is equal to Q naught E to the minus T over RC, and then similarly from that we had I is equal to I naught E to the minus T over RC, or even V is equal to V naught E to the minus T over RC, and those of course are all examples of exponential decays or exponential decreases. So that's it for this video then. As I said, in the next video what we're going to do is we're really going to delve into these equations, and especially that exponential decay, exponential decrease part of it, so the e to the minus t part of it, and hopefully understand that a little bit more, understand exactly what's going on, especially from a mathematical point of view. But of course, as usual, thanks for watching. I hope you found that useful, and I'll see you in the next video.